মালদা কলেজ, 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 মালদা কলেজ।
ছোট ছোট স্রোতধারা মিশে যে নদী সাগর চেনায়,
অবিরাম তার গতিধারা নিয়ে যায় দুর্মোহনায়।
আঁকে বাঁকে প্রাণোচ্ছ্বাস যৌবনের উতল বাতাস, আঁকে বাঁকে প্রাণোচ্ছ্বাস যৌবনের উতল বাতাস।
আলোর অক্ষর জাগে জীবনের গাঢ় আশ্বাস।
মালদা কলেজ, মালদা কলেজ,
বুকে রাখি তোমার ইতিহাস।
মালদা কলেজ, মালদা কলেজ,
বুকে রাখি তোমার ইতিহাস।
অধুনা বাংলাদেশের দাদুন চকে পথ চলা শুরু, সে পথ মেলালো মালদায় ছাত্র ও শিক্ষা গুরু। অধুনা বাংলাদেশের দাদুন চকে পথ চলা শুরু, সে পথ মেলালো মালদায় ছাত্র ও শিক্ষা গুরু।
শিক্ষালয় মানে
কত প্রতিভার প্রকাশ,
শিক্ষালয় মানে
শত পুষ্পের বিকাশ।
শিক্ষালয় মানে
কত প্রতিভার প্রকাশ,
শিক্ষালয় মানে
শত পুষ্পের বিকাশ। সময়ের স্রোতে থেকে আবহমান আগামীর আলো উদ্ভাস।
মালদা কলেজ, মালদা কলেজ,
হৃদয়ে জ্ঞানের চাষবাস।
মালদা কলেজ, মালদা কলেজ,
বুকে রাখি তোমার ইতিহাস।
কলেজ ক্যাম্পাসে ঘুরে জীবনের কম্পাস, হাজার
কলেজ থেকে বেরিয়ে গেছে, সুবর্ণ আসছে। আমরা এখানে দেখতে পাবো সুবর্ণকে, আমরা তাকে ফুল দিয়ে বরণ করব, আমরা দেখতে পাবো। আপনারা কেউ উঠবেন না, আমরা বসেই তাকে, যখন ও ঢুকবে আমি প্রত্যেককে অনুরোধ করব আমরা করতালি দিয়ে বসেই আমরা তাকে অভিনন্দন জানাবো, স্বাগত করব। কলেজের অডিটোরিয়ামে প্রবেশ করেছে।
সুস্বাগতম, স্বাগতম, সুস্বাগতম, তব স্বাগতম, সুস্বাগতম। কিশোর কিশোরী এসো, তরুণ তরুণী এসো, মেনে চলে প্রভুর নিয়ম। স্বাগতম, সুস্বাগতম, তব স্বাগতম, সুস্বাগতম।
চলে এসছেন, আমি মঞ্চে ডেকে নিচ্ছি আমাদের গভর্নিং বডির অন্যতম সদস্য কাউন্সিলর চৈতালি ঘোষ সরকারকে। সুবর্ণ প্রবেশ করছে।
আলোক থেকে এসেছে যে বার্তা তাহার, মানলে তাকে, মানলে তুমি, কাটবে মনের আধার। দিব্যলোকের আলোক থেকে এসেছে যে বার্তা তাহার, মানলে তাকে,
তোমরা এই সাইডে যাবে, ওইখান দিয়ে যাবে, এই সিঁড়িতে উঠবে, ওইদিকে গিয়ে ওদিকে নেমে এখান দিয়ে আসবে।
তিনি তোমাদের জন্য মানলে তাকে তুমি হবে যে ধন্য। স্বাগতম সুস্বাগতম তব স্বাগতম সুস্বাগতম।
সুবর্ণ আসছে, শঙ্খধ্বনি দিয়ে পুষ্পার্ঘ ছড়িয়ে আমরা সুবর্ণকে স্বাগত জানাচ্ছি। মালদা কলেজের এনএসএস এবং এনসিসি ভলেন্টিয়াররা এবং গার্ড অফ অনার দিয়ে আসছে মালদা কলেজের এনসিসির ক্যাডাররা। মালদা কলেজ অডিটোরিয়ামে সুবর্ণ চলে এসেছে, আমরা তাকে স্বাগত জানাচ্ছি। মালদা কলেজের এনএসএস এনসিসি ভলেন্টিয়াররা তাকে গার্ড অফ অনার দিয়ে এবং পুষ্পবৃষ্টি করে তাকে আমরা স্বাগত জানাচ্ছি। সুবর্ণ আইজাক বাড়ি, প্রফেসর সুবর্ণ আইজাক বাড়ি, প্রফেসর সুবর্ণ আইজাক বাড়ি। আপনারা কেউ উঠবেন না, করতালি দিয়ে আমি অনুরোধ করছি, করতালি দিয়ে তাকে স্বাগত জানান। হাততালি দিয়ে বসে সুবর্ণ আইজাক বাড়ি, সুবর্ণ আইজাক বাড়ি, সরে যাবেন। সুবর্ণ আইজাক বাড়ি চলে এসেছেন। সুবর্ণ আইজাক বাড়ি, প্রফেসর সুবর্ণ আইজাক বাড়িকে আমরা স্বাগত জানাবো। প্লিজ আমরা সুবর্ণ আইজাক বাড়ি আপনাদের পাশ দিয়ে আসছে। আপনারা দেখুন, বিস্ময় ভালো গড অফ ম্যাথস সুবর্ণকে স্বাগত জানান, হাততালি দিয়ে স্বাগত জানান।
কিশোর কিশোরী এসো, তরুণ তরুণী এসো, মেনে চলে প্রভুর নিয়ম।
সবাইকে স্বাগত।
স্বাগতম
প্রফেসর সুবর্ণ বাড়ি, এদিকে এদিকে সুবর্ণ, প্রফেসর সুবর্ণ আইজাক বাড়িকে হাততালি দিয়ে আপনারা স্বাগত জানান। আমাদের সৌভাগ্য, আমরা বিস্ময় বালককে কাছে পেয়েছি। এই বিস্ময় বালকের সঙ্গে একই মঞ্চে তার সঙ্গে থাকা এটা সত্যি সৌভাগ্যের। আমরা সুবর্ণ আইজাক বাড়িকে আমরা অভিনন্দন জানাচ্ছি, করতালি দিয়ে তাকে স্বাগত জানাচ্ছি। সবাই করতালি দিয়ে তাকে স্বাগত জানান। সুবর্ণ আইজাক বাড়ি, সুবর্ণ আইজাক বাড়ি আমি মঞ্চে ডেকে নিচ্ছি আমাদের মালদা কলেজের পরিচালন সমিতির সভাপতি অধ্যাপক সৌরেন বন্দ্যোপাধ্যায় মহাশয়কে, এবং আমি ডেকে নিচ্ছি আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য মহাশয়কে। আমি ডেকে নিচ্ছি প্রফেসর সুবর্ণ আইজাক বাড়িকে। আমি ডেকে নিচ্ছি প্রফেসর সুবর্ণ আইজাক বাড়ির পিতা প্রফেসর রশিদুল বাড়িকে, এবং আমি ডেকে নিচ্ছি প্রফেসর প্রাণেশ দেবনাথ মহাশয়কে। আমি ডেকে নিচ্ছি প্রফেসর স্নেহময় ঘোষ মহাশয়কে। মালদা কলেজের পক্ষ থেকে আমরা ওনাকে স্বাগত জানাচ্ছি। আমরা শুরুতেই আমি আপনাদের আমি মঞ্চে ডেকে নিচ্ছি মাননীয় রেজিস্ট্রার অধ্যাপক বিশ্বজিৎ দাস মহাশয়কে। হ্যাঁ, এবং আমাদের মঞ্চে আছেন মালদা কলেজের গভর্নিং বডি সদস্য তথা ইংরেজবাজার পৌরসভার ভাইস চেয়ারম্যান শ্রীমতী সুমলা আগরওয়াল মহাশয়। এবার আমি আমাদের আমি এবার আমাদের পরনের পালা। আমি অনুরোধ করব আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্যকে আর আমার কলেজের অধ্যাপিকাদের আমি অনুরোধ করব মঞ্চে আসার জন্য। কলেজের তরফ থেকে আমরা প্রথমে আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য বরণ করে নেবেন আজকের আমাদের প্রধান অতিথি এবং বিস্ময় বালক, ম্যাথস অফ গড প্রফেসর সুবর্ণ আইজাক বাড়িকে উত্তরীয় পরিয়ে ফুলের তোড়া এবং মেমেন্টো দিয়ে তাকে বরণ করে নিচ্ছে আমাদের মালদা কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য। এবার আমরা বরণ করে নেব প্রফেসর সুবর্ণ কুমার বাড়ির বাবা প্রফেসর। আচ্ছা, এবার আমরা বরণ করে নেবেন আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য প্রফেসর সুবর্ণ আইজাক বাড়ির পিতা প্রফেসর রশিদুল বাড়ি মহাশয়কে আমি সকলকে হাততালি দিয়ে অভিনন্দন জানানোর জন্য অনুরোধ করছি। আমরা যিনি না হলে আমরা আজকে আপনাদের সামনে প্রফেসর সুবর্ণ বাড়িকে হাজির করতে পারতাম না, প্রফেসর প্রাণেশ দেবনাথকে আমরা বরণ করে নিচ্ছেন আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য। আরেকজন প্রফেসর স্নেহময় ঘোষকে বরণ করে নিচ্ছেন আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য। এবার আমরা বরণ করে নেব গৌড়বঙ্গ বিশ্ববিদ্যালয়ের রেজিস্ট্রার অধ্যাপক বিশ্বজিৎ দাস মহাশয়কে আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য আমাদের মাননীয় গৌড়বঙ্গ বিশ্ববিদ্যালয়ের রেজিস্ট্রারকে বরণ করে নিচ্ছেন। এবার আমরা বরণ করে নেব রাজ্যের প্রাক্তন ক্যাবিনেট মন্ত্রী তথা ইংরেজবাজার পৌরসভার চেয়ারম্যান মাননীয় শ্রী কৃষ্ণেন্দ্র নারায়ণ চৌধুরীকে বরণ করে নেবেন আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য মহাশয়। এবার বরণ করে নেব আমাদের মালদা কলেজ পরিচালন সমিতির সভাপতি অধ্যাপক সৌরেন বন্দ্যোপাধ্যায় মহাশয়কে বরণ করে নেবেন আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্য। এবার আমরা বরণ করে নেব ইংরেজবাজার পৌরসভার ভাইস চেয়ারম্যান তথা মালদা কলেজ পরিচালন সমিতির সদস্য মাননীয় শ্রী সুমলা আগরওয়াল মহাশয়কে। এবার আমরা বরণ করে নেব মালদা কলেজ পরিচালন সমিতির আরেকজন সদস্য তথা ইংরেজবাজার পৌরসভা কাউন্সিলর শ্রীমতী চৈতালি ঘোষ সরকার মহাশয়কে। অতিথিদের বরণ শেষে আমরা এবার প্রত্যেককে আমরা দাঁড়াতে বলবো। আচ্ছা, আমাদের মহানাগরিকের পক্ষ থেকে আমাদের চেয়ারম্যান মাননীয় শ্রী কৃষ্ণেন্দ্র নারায়ণ চৌধুরী বরণ করে নেবেন আমাদের প্রফেসর সুবর্ণ আইজাক বাড়িকে। এবার আমরা অনুষ্ঠানের শুরুতেই আমরা স্টেট সং গাইব। আমাদের মিউজিক প্রত্যেককে আমি বলবো মঞ্চে এবং মঞ্চের বাইরে দাঁড়াতে আমাদের স্টেট সং হবে। প্লিজ স্টার্ট। ধন্যবাদ। সবাই আসন গ্রহণ করুন। এবার আমাদের প্রথাগত আমরা আমাদের দুটো সেশনে ভাগ করেছি, ইনাগুরাল সেশন অ্যান্ড ইন্টারঅ্যাক্টিভ সেশন। এবার আমাদের উদ্বোধনী সঙ্গীত গাওয়ার জন্য অনুরোধ করছি আমাদেরই ছাত্রী সুনন্দা চক্রবর্তীকে। সুনন্দা চক্রবর্তী উদ্বোধনী সঙ্গীত গাইবেন।
হ্যালো হ্যালো সূর্য তারা বিশ্ব
আমরা খুব সংক্ষিপ্ত সময়ের মধ্যেই আমরা ইনাগুরাল প্রথম যে পর্যায়টা শেষ করব। এবার আমাদের আজকের অনুষ্ঠানে স্বাগত ভাষণ দেওয়ার জন্য আমি অনুরোধ করছি আমাদের কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্যকে।
On behalf of Malda College, I feel truly honored and delighted to welcome you all to this historic occasion in the academic journey of our institution. Today is not another program. It is a rare and unforgettable moment for all of us gathered here. First and foremost, let us extend our heartfelt welcome to Professor Subarna Bari, the youngest professor in the world. His extraordinary achievements and unwavering dedication and passion to mathematics, physics, and science have inspired students, teachers, researchers across the globe. We are deeply grateful for his presence among us today. Friends, let us all put our hands together for a big round applause to welcome Professor Bari. We are equally honored to welcome his father, Mr. Rashidul Bari, who has always been a pillar of support in nurturing this genius mind. We also warmly welcome the two guiding members of Team Professor Bari, Mr. Pranesh Devnath and Professor Snehumoy Ghosh. I also take this opportunity to warmly welcome our distinguished guest, Professor Souren Bandyopadhyay, Honorable President, Malda College Governing Body, and the former Vice Chancellor of West Bengal State University and Professor of University of Gaurbango. Professor Bishwajit Das, Registrar in Charge, University of Gaurbango. Sri Krishnendu Narayan Chaudhuri, Honorable Chairman, English Bazar Municipality, and a great well-wisher of Malda College. Shrimati Chaitali Ghosh Sarkar, Chairperson Malda District TMC, and Honorable Governing Body Member of Malda College. Please, big clap. Shrimati Shumala Agarwala, Vice Chairman English Bazar Municipality, and Honorable Governing Body Member of Malda College. And now, extend a very special welcome to all of you, our beloved students, esteemed faculty members, respected principals, headmasters, distinguished doctors from various institutions, invited guests, staff members, and all science enthusiasts who have joined us today. Most importantly, today Malda College is blessed with the extraordinary presence of a true wonder of the academic world, Subarna Bari, born 9th April 2012, is recognized as a child prodigy with the exceptional talents in the science field. It is indeed a matter of great pride for all of us. Such a young genius is here to share his knowledge with us. He will be speaking on a very fascinating and advanced topic in physics, Bose-Einstein statistics, a subject that connects the genius of Satyendranath Bose and Albert Einstein. This program is not only for the students of Malda College, but also for the young, brilliant minds who have joined us from the different schools, colleges, and university of the entire Malda district. Your enthusiasm and curiosity make this occasion even more meaningful. Dear students, remember the moments like these are rare. Let this inspire you to dream big, to push boundaries, and to realize that no dream is beyond your reach. Let us open our minds, learn with curiosity, carry forward the spirit of knowledge with the guiding motto of Malda College, learn together, grow together. On behalf of Malda College, I once again extend my warmest welcome to all of you. Let us make this day a milestone in the history of our Malda College and in the academic journey of every student present here. Thank you all.
ধন্যবাদ মালদা কলেজের অধ্যক্ষ ডক্টর মানস কুমার বৈদ্যকে। এবার আমি বক্তব্য রাখার জন্য অনুরোধ করছি আমাদের গৌরবঙ্গ বিশ্ববিদ্যালয়ের রেজিস্ট্রার মাননীয় ডক্টর বিশ্বজিৎ দাস মহাশয়কে। আমরা খুব সংক্ষিপ্ত ভাষণ দিয়ে আমরা এই প্রথম পর্যায়ে শেষ করি। আমরা যার জন্য এসেছি বাড়ির আমরা ক্লাস দেখব।
নমস্কার। উপস্থিত মঞ্চে যারা আমার শ্রদ্ধেয় ব্যক্তিত্ব আছেন তাদেরকে আমার শ্রদ্ধা জানাচ্ছি। মঞ্চের পাশে যারা শ্রদ্ধেয় ব্যক্তিত্ব আছেন তাদের শ্রদ্ধা জানাচ্ছি। সমবয়সীয় ছোটদের আমার শুভেচ্ছা ভালোবাসা জানাচ্ছি। আজকে সত্যিই একটি ঐতিহাসিক দিন। প্রফেসর বারিক আমাদের মালদা কলেজে বক্তৃতা করতে এসছেন এবং গৌরবঙ্গ বিশ্ববিদ্যালয়ে তিনি যাবেন। আমরা গৌরবঙ্গ বিশ্ববিদ্যালয়ের পরিবারের পক্ষ থেকে 26টি কলেজের ছাত্রছাত্রী, শিক্ষক, শিক্ষাকর্মী এবং সকলের পক্ষ থেকে প্রফেসর বারিককে আমাদের উষ্ণ অভিনন্দন জানাচ্ছি। তাকে এখানে নিয়ে আসার ক্ষেত্রে যারা সহায়তা করেছেন তাদের সকলকেই আমাদের শুভেচ্ছা। আজকের এই অনুষ্ঠান, এই মহতী অনুষ্ঠান আয়োজন করে মালদা কলেজ যে কৃতিত্বের স্বাক্ষর রেখেছেন, সেই কৃতিত্ব তখনই বাস্তবায়িত হবে যদি আমাদের পরবর্তী প্রজন্ম, আজকে উপস্থিত ছাত্রছাত্রীরা তাকে দেখে উদ্বুদ্ধ হন এবং বিজ্ঞান চর্চায় নিয়োজিত থাকেন। তার সম্পর্কে যাই বলি না কেন অপ্রতুল মনে হবে। আমি সময় নষ্ট করব না। আবারও প্রফেসর বারিক এবং তার সঙ্গে যারা এসছেন প্রত্যেককে আমার শ্রদ্ধা এবং উপস্থিত সকল ছাত্রছাত্রীদের আমার শুভেচ্ছা এই জানিয়ে আমার কথা শেষ করছি। ধন্যবাদ।
ধন্যবাদ গৌরবঙ্গ বিশ্ববিদ্যালয়ের মাননীয় রেজিস্ট্রার ডক্টর বিশ্বজিৎ দাসকে। এবার আমরা সংক্ষিপ্ত বক্তব্য শুনে নেব আমাদের ইংরেজবাজার পৌরসভার মাননীয় পৌর প্রধান তথা রাজ্যের প্রাক্তন ক্যাবিনেট মন্ত্রী শ্রী কৃষ্ণেন্দ্র নারায়ণ চৌধুরী মহাশয়ের কাছে।
আজকের দিনটা আমাদের কাছে খুব স্মরণীয় হয়ে থাকবে। মালদা কলেজের তার কাজকর্মের মধ্যে সুবর্ণর আশাটা স্বর্ণাক্ষরে লেখা থাকবে, এটা আমি মনে করি। মালদা কলেজে অনেক বরেণ্য মানুষ এসেছিলেন, তার মধ্যে মহামহিম রাষ্ট্রপতি প্রণব মুখার্জি এসেছিলেন। তিনি এই কলেজের জন্য, এই অডিটোরিয়ামের জন্য অনেক কিছু করে দিয়েছিলেন। আর তারপরেই একটা ইন্টারন্যাশনাল ফিগার সুবর্ণ তিনি পদার্পণ করলেন, যাকে আমরা বলি অবাক বালক। এত অল্প বয়সে যাকে বলে জুনিয়র আইনস্টাইন, সে এসছে। তার সঙ্গে যারা প্রফেসর এসছেন তাদের আমি আন্তরিক ধন্যবাদ জানাচ্ছি। এই কলেজের প্রেসিডেন্টকে জানাচ্ছি ধন্যবাদ, আমাদের প্রিন্সিপালকে জানাচ্ছি, আমাদের দুই কলিগ চৈতালি, সুমলা আমার রেজিস্ট্রার আছেন। সুবর্ণর বাবাকে আরও বেশি করে ধন্যবাদ জানাচ্ছি। প্রথমে সুবর্ণ হচ্ছে আমাদের বাঙালি, সে আমেরিকাতে জন্মগ্রহণ করলে বাঙালির টানটা তার মধ্যে আছে। You know Bengali? Little more. Thank you. এটাই ধন্য। ওর বাবা একটা ইন্টারভিউ দেখছিলাম কিছুদিন আগে, যে বাংলাদেশ থেকে কিভাবে এসছে। ও বললো সেই সময় বাংলাদেশে আমার পয়সা ছিল না বাইরে যাওয়ার, কিন্তু সে আমেরিকাতে এস্টাবলিশ করেছে। আর তার সুযোগ্য সন্তান আমাদের সকলের বাঙালির মুখ উজ্জ্বল করছে। তাকে আবার আমি ধন্যবাদ জানাচ্ছি। আমি এইটুকু আশা করব, এই বাংলা থেকে অনেক বড় বড় মানুষ যারা বিশ্বব্যাপী খ্যাতি অর্জন করেছিলেন, তারা যেমন সেই বাঙালি পানাটাকে রেখেছেন, আমার সুবর্ণ সেইভাবে বাঙালি পানা থাকবে। আমি বিশ্বাস করি সে আমেরিকাতে জন্মগ্রহণ করলে আমেরিকার টান থাকবে না, থাকবে বাংলার টান। তাকে আমি ধন্যবাদ জানাচ্ছি। আর এটুকু আশা করব, যেভাবে আইনস্টাইন সারা পৃথিবীর মানুষকে আকর্ষিত, সুবর্ণ হয়তো তারও রূপরেখাকে আরও টপকে যাবে। ধন্যবাদ, সবাই ভালো থাকুক, এটাই কামনা করি। থ্যাংক ইউ।
ধন্যবাদ মাননীয় শ্রী কৃষ্ণেন্দ্র নারায়ণ চৌধুরীকে। এবার আমি ডেকে নেব গড অফ ম্যাথস সুবর্ণ আইজাক বাড়ির বাবা পিতা প্রফেসর রশিদুল বাড়িকে দু চারটি কথা বলার জন্যে। রশিদুল বাড়ি, আমি রশিদুল বাড়ি স্যারকে বলবো আপনি বাংলায় বলুন। থ্যাংক ইউ স্যার, থ্যাংক ইউ।
নমস্কার। বারবার ভারতবর্ষে ফিরে আসি কারণ ভারতবর্ষের চেয়ে শ্রেষ্ঠ দেশ কোথাও নেই। আমরা যখন আসলাম 24শে অগাস্ট কলকাতা এয়ারপোর্টে যখন নামলাম, তখন আমাদের ভেতরের বাঙালিটা কেমন জানি জেগে উঠল। এয়ারপোর্টে প্রথমে দেখলাম রবীন্দ্রনাথ ঠাকুরের ছবি, চোখে পানি এসে গেল, কারণ রবীন্দ্রনাথ ঠাকুর মানেই তো বাঙালি, কাজী নজরুল মানেই তো বাঙালি, বাঙালি মানেই তো জগদীশচন্দ্র বসু, বাঙালি মানেই তো সত্যেন্দ্রনাথ বসু, বাঙালি মানেই তো প্রণব মুখার্জি। স্যার বললেন একটু আগে বাঙালি মানেই তো স্বামী বিবেকানন্দ, বাঙালি মানেই তো নেতাজি সুভাষচন্দ্র বসু, বাঙালি মানেই তো অমর্ত্য সেন। একটু আগে একজনে অমর্ত্য সেনের লেখা একটা বই দিলেন সুবর্ণকে দেওয়ার জন্য। এই যে ভারতবর্ষ এক সময় 500 সালে, 600 সালে, 700 সালে ভারতবর্ষের গোল্ডেন এজ ছিল। এরপর নানা কারণে গোল্ডেন এজ চলে গেল, কারণ বাইরের লোক এসে ভারতবর্ষ আক্রমণ করলো। আর্যভট্টা পৃথিবীকে ডেসিমল দিয়েছিলেন এই ভারতবর্ষ থেকে, ব্রহ্মগুপ্ত পৃথিবীকে শূন্য দিয়েছিলেন এই ভারতবর্ষ থেকে। এরপরে দীর্ঘ 1000 বছর ভারতবর্ষে কিছু হয়নি, কারণ বিদেশিরা ভারতবর্ষকে শোষিত করেছে। এরপর ভারতবর্ষে গোল্ডেন এজ আবার ফিরে এসেছে বাঙালির হাত ধরে। রবীন্দ্রনাথ ঠাকুরকে দিয়ে শুরু হয়, এরপর সত্যেন্দ্রনাথ বসু, স্যার জগদীশচন্দ্র বসু, এদের মাধ্যমে বাঙালি ভারতবর্ষকে আবার গোল্ডেন এজ ফিরিয়ে দেয়। সেই বাঙালির স্বর্গে এসে পশ্চিমবঙ্গে আমাদের নিজেদের ধন্য মনে হচ্ছে আমাদেরকে বরণ করে নেওয়ার জন্যে। বাঙালির মধ্যে কি আছে সেটা হয়তো বাঙালি জানে না। বাঙালি ভারতবর্ষের হারানো গৌরব ফিরিয়ে দিয়েছিল সেই গোল্ডেন এজ। সত্যেন্দ্রনাথ বসু, সুবর্ণ আজকে তার উপর বক্তব্য দেবে, তার মাধ্যমে ভারতবর্ষে বিজ্ঞানের স্বর্ণযুগ শুরু হয়েছে। তিনি সারা বিশ্বকে তার বিজ্ঞান দিয়ে পরিবর্তন করে দিয়েছেন। মহাবিশ্বে ফার্মিয়ন্স যদি 50% থাকে, তাহলে বোসনও 50% আছে। আমাদের সেই বসু, আমাদের সেই প্রাণের সত্যেন্দ্রনাথ বসু, তিনি এই বাংলায় জন্মগ্রহণ করেছেন। ভারতবর্ষ সুবর্ণকে যেটা দিয়েছে সেটা আর কেউ দেয়নি। সুবর্ণ যখন বয়স 7 বছর, তখন ভারতবর্ষের আরেকজন মহান মানব, নোবেল লরিয়েট কৈলাস সাথিয়ার্থী, তিনি সুবর্ণকে গ্লোবাল চাইল্ড প্রডিজি দিয়েছেন। সেই 2019 সালে পুনে ইউনিভার্সিটি, তার একটা বিখ্যাত ইউনিভার্সিটি ভারতবর্ষের, গ্র্যাজুয়েট স্টুডেন্টের সামনে দাঁড়িয়ে দিয়েছে বক্তব্য দেওয়ার জন্য। পৃথিবীর কোথায় এটা সম্ভব না। মুম্বাই ইউনিভার্সিটি, ব্রিটিশরা ভারতবর্ষে 6টা ইউনিভার্সিটি করেছিল, তার মধ্যে কলকাতা ইউনিভার্সিটি ছিল একটা, মুম্বাই ইউনিভার্সিটি ছিল আরেকটা। সেই মুম্বাই ইউনিভার্সিটি 7 বছরের সুবর্ণকে গ্র্যাজুয়েটদের ফিজিক্স পড়ানোর জন্য দিয়েছিল। একটুও ভাবছিল না 7 বছরের একটা শিশু কিভাবে এটা পারবে, সেটা ভাবেনি, কারণ এটা ভারতবর্ষ। এখানে বিজ্ঞানের, এখানে জ্ঞানের দাম আছে। বয়সের, কার বয়স কত, এটা ভারতবর্ষ দেখে না। সেই জন্য আমি যখনই সুযোগ পাই তখন ভারতবর্ষ, আপনারা যারা জন্মগ্রহণ করেছেন তাদের মনে করিয়ে দিই, আপনাদের মতো ভাগ্যবান মনে হয় কেউ নেই। আমি এটা বলি এই জন্য, আমি এটা দাদাকে মনে হয় কয়েক হাজারবার বলেছি যে আপনার শিশুদের স্মরণ করিয়ে দেবেন, তারা পৃথিবীর শ্রেষ্ঠ জায়গায় জন্মগ্রহণ করেছে। ভারতবর্ষ যদি একজন যুক্তরাষ্ট্রের একজন বাচ্চাকে এত সুযোগ দিতে পারে যেটা পৃথিবীর কেউ দেয়নি, তাহলে ভারতবর্ষ, আপনারা যারা ভারতবর্ষে জন্মগ্রহণ করেছেন, আপনাদের শিশুরা যারা ভারতবর্ষে জন্মগ্রহণ করেছেন, তারা না কত সৌভাগ্যবান। আমি তাদের দিকে তাকিয়ে থাকি, মাঝে মধ্যে জেলাস হয়ে যাই, কারণ তাদের যেটা আছে হয়তো আমার সেটা নেই। তারা ভারতবর্ষে জন্মগ্রহণ করেছে, এত সৌভাগ্যবান, এত সৌভাগ্যের আর কি হতে পারে। 28টা রাজ্য আছে ভারতবর্ষের, সুবর্ণ প্রায় বেশিরভাগই গিয়েছে বক্তব্য দেওয়ার জন্য। কোনো রাজ্যের মানুষের সাথে কোনো রাজ্যের পার্থক্য খুঁজে পাই নাই। সবার একজনের আত্মা মনে হয় আরেকজনের আত্মার চেয়ে বড়। এত সুন্দর দেশ, এত এত বন্ধুর দেশ পৃথিবীতে কোথাও খুঁজে পাওয়া যাবে না। সুবর্ণ সৌভাগ্যবান, ভারতবর্ষে সুবর্ণকে বরণ করে নিয়েছিল, নাহলে সুবর্ণ আজকের এ পর্যায়ে আসতে পারতো না। আমি আপনাদের সবাইকে, ভারতবর্ষবাসীকে ধন্যবাদ জানাচ্ছি। সুবর্ণ সবসময় তার বক্তব্য সেই জন্য ভারতের জাতীয় সঙ্গীত রবি ঠাকুরের সেই অমর গান দিয়ে শুরু করে। আপনারা যা করেছেন সুবর্ণের জন্য, সেই জন্য অনেক ধন্যবাদ। আপনাদেরকে নমস্কার।
অসংখ্য ধন্যবাদ সুবর্ণ আইজাক বাড়ির পিতা প্রফেসর রশিদুল বাড়িকে। এবার আমি ডেকে নেব আমাদের মালদা কলেজ পরিচালন সমিতির সভাপতি অধ্যাপক সৌরিন বন্দ্যোপাধ্যায়কে। আপনাদের আমি জানিয়ে রাখি, আমাদের সভাপতির বক্তব্যের পরই প্রফেসর সুবর্ণ বাড়ি শুরু করবে, এবং আমি আপনাদেরকে বলেছিলাম প্রশ্নগুলো দিতে আমাদের এনসিসিদের কাছে আমরা নিয়ে আসব, এবং আমাদের আজকে যেভাবে শুরু হয়েছে আমরা শেষ করব জাতীয় সঙ্গীত গেয়ে। লাস্ট আপনারা জাতীয় সঙ্গীত না হওয়া পর্যন্ত কেউ যাবেন না। স্যার প্লিজ, অধ্যাপক সৌরিন বন্দ্যোপাধ্যায় স্যার।
ওয়েলকাম সুবর্ণ আইজাক বাড়ি। মঞ্চে উপবিষ্ট বিশিষ্টজন সকলকে শ্রদ্ধা। সামনে যারা বিশিষ্ট মানুষ রয়েছেন, মাননীয় অধ্যাপক অধ্যাপিকা, বাইরে থেকে আগত মাননীয় শিক্ষক শিক্ষিকা, স্নেহের ছাত্রছাত্রী, সকলকে আমার পক্ষ থেকে আন্তরিক শুভেচ্ছা অভিনন্দন। আমরা যে জন্যে এসেছি সেটা মুখ্য। আমি মনে করি আমি কথা বাড়াবো না। রবীন্দ্রনাথকে দেখে যেমন বলা হয়েছিল, তোমার প্রতি চাহিয়া আমাদের বিস্ময়ের সীমা নাই, আমরা সুবর্ণ আইজাক বাড়িকেও বলছি যে তোমার প্রতি চাহিয়া আমাদের বিস্ময়ের সীমা নাই। আমরা মনে করি এই যে এতক্ষণ কথা হয়েছে, তার মধ্যে একটি কথা বলার, সুবর্ণের একটি বই আছে, তার নাম দ্য লাভ, ভালোবাসার জন্য সে পৃথিবীতে আজকে বিজ্ঞান সচেতন মানুষের কাছে জীবন বোধকে পৌঁছে দিতে চায়। আমরা শুধু মালদাবাসী নয়, পশ্চিমবঙ্গবাসী নয়, সমগ্র ভারতবাসী তাকিয়ে আছি তার কথা শোনার জন্য। ধন্যবাদ জানাই এবং একই সঙ্গে আবার বলি ওয়েলকাম সুবর্ণ আইজাক বাড়ি।
ধন্যবাদ মালদা কলেজ পরিচালন সমিতির সভাপতি অধ্যাপক সৌরিন বন্দ্যোপাধ্যায়কে। এরপরে এ ব্রিফ introduction of Professor Bari, Professor Dr. UK Uttam Kumar Sarkar. Please, Dr. Sarkar.
Ladies and gentlemen, very good afternoon. We all are eagerly waiting for the speech of Professor Subarna Isaac Bari. Before that, I, on behalf of organizing committee, would like to give a brief introduction. I may miss some important points about him, as well as some information may be incomplete. If that happens unwillingly, I must apologize in advance. Professor Subarna Isaac Bari, as you see, the sweet, cute, handsome and lovely boy of 13 is now worldwide known as Einstein of our time, world's youngest professor, global child prodigy, god of math. He is an extraordinary young genius who has amazed people with his brilliance in mathematics, science, and education. Professor Bari is a child prodigy, a teacher, an author, and peace advocate. He was born on April 9, 2012 in New York City, USA. As a toddler, he showed signs of a genius. By age 2, he had surprisingly memorized periodic table. At 4, he was recognized by President Barack Obama for his outstanding knowledge of math and science. At 6, Harvard University honored him for solving advanced math and physics problems. At 8, Nobel laureate Kailash Satyarthi presented him Global Child Prodigy Award. And by 9, he completed his middle school, which is upper primary in our state. At 12, he graduated from Malvern High School in New York. And at present, he has begun studying mathematics and physics at New York University on a full scholarship. He also teaches, he is a student in New York University, and at the same time, he teaches calculus at New York University, becoming the youngest university level instructor in the US. He plans to graduate from bachelor's program by 2026 and aims to complete his PhD by 2028. His parents, Professor Rashidul Bari and Shaheda Bari, are initially from Bangladesh, but now settled in United States. His father is an educator, writer, mathematician, while his mother deeply supports Subarna's journey. His parents noticed his talent early and started teaching him complex topics in science and mathematics. They helped him grow in an environment filled with books, curiosity, and learning. His elder brother, Rifat Bari, is also an integral part in this venture. Professor Bari is invited to speak at prestigious institutions like IITs in India. It's a proud privilege of Malda College to host this scientific lecture of Professor Bari. We are the first general degree college in West Bengal and most probably in India too to host such a program. Professor Subarna Bari wrote a book titled The Love, which promotes peace, kindness, and global unity. His writing discusses terrorism, human rights, and the importance of spreading love in a world full of hate. Professor Subarna Bari's biography is more than just a story about a genius. It's a story about a passion, family support, kindness, and a dream to improve the world through education. Starting from memorizing the periodic table at the age of 2 to teaching at New York University by age 13, Subarna Bari has proven that age does not define ability. His journey is a source of inspiration for young minds and adults across the globe. We love you so much, and at the same time, we respect you, Professor Subarna Bari. Now it's time to begin the much-awaited lecture on Satyendranath Bose, from quantum theory to Bose-Einstein statistics. This is a statistics of indistinguishable integral spin particles called bosons, and it leads to the fifth state of matter, a state after solid, liquid, gas, and plasma. And this fifth state of matter is known as Bose-Einstein condensates. Also, other significant phenomena like superfluidity and superconductivity. Thus, the lecture will be very much interesting and we shall be definitely enriched. Also, we have requested Professor Bari to discuss the elementary number theory, as many of the students present here are very much interested in this topic too. With these few words, I conclude. Thank you all for your patient hearing. I now heartily invite Professor Subarna Isaac Bari to please deliver his lecture. Let us welcome Professor Bari with a big round of applause.
Thank you. Thank you, Dr. উত্তম কুমার সরকার। এবার আমি আমাদের মঞ্চের অতিথিদের সামনে বসার জন্য আমি করব। ওকে।
Thank you.
So please test yourself.
Am I audible? Am I audible? No, no. Okay. Okay, this is enough. Okay. Microphone check, microphone check. Okay. Thank you. When should I begin?
Introduction is all right?
Yes, yes. Thank you. Okay.
Please start.
Thank you. Namaskar, everybody. I am so excited to be here at Malda College today and to be lecturing about quantum mechanics to you all. Now, truthfully, I did pick to lecture on the works of Satyendranath Bose, one of the most famous scientists in history, and possibly the most famous scientist from West Bengal, partly because I'm lecturing in West Bengal, but not fully, because Bose's work deserves merit just outside that. Bose's work is up there with some of the pioneers of quantum mechanics. Paul Dirac, Bohr, Einstein. I mean, he even collaborated with Einstein on some of the most important and fundamental works that define the middle stage of quantum mechanics. And today, I want to show that to you in the simplest way possible. So let's start with something called the Pauli exclusion principle. Is this visible? Okay. I'm going to start here. Where's the... Okay, thank you. The Pauli exclusion principle is one of the fundamentally defining principles of quantum mechanics. See, in quantum mechanics, usually we have to study systems where two particles are interacting with one another. Because the real world doesn't consist of just one elementary particle, it consists of millions of millions of millions of millions and so on and so forth. So, at some point you had to study how these particles interact with one another. Now, just like classical mechanics, where all motion is dictated by Newton's second law, F is equal to ma, or if you want to be more precise, you can write it like this. This right here is the fundamental law of classical mechanics. And when we want to describe a system in classical mechanics where two objects are interacting with one another, say gravitationally, like in the two-body problem, then we want a function of position that captures both at once. So we want to know where each of them is, because their own positions will influence the other body's position, which will in turn influence their own position, and so on and so forth. So you have to translate that to quantum mechanics. But how? Well, in quantum mechanics, we no longer for sure know the position of a particle. In classical mechanics, or the mechanics that you learn in school, you can always pinpoint exactly where a particle is at a certain point in time. In quantum mechanics, we can't be so sure of this certainty. What we instead measure is something called a wave function, which is traditionally represented with the letter psi.
A wave function is like a probability density function. What that means is that it does not tell us where the particle is. That is not possible in quantum mechanics. You can measure where the particle is, but the problem is you will always get some level of uncertainty. For example, in one measurement, you might get 0.235, in another measurement, you might get 0.212, in another, you might get 0.265. And the point of quantum mechanics is not that you can't make these measurements, it's that you will never get them to be 100% reliable. Just as the famous uncertainty principle says, the more you know about an object's position, the less you know about its momentum. All that means is, the more certain you are about its position, say you pinpoint all of the position measurements to give you the exact same quantity, suddenly all the momentum measurements will be totally off from one another. That is essentially the message of quantum mechanics. So how do we measure this uncertainty? Well, we use a tool from probability, what we call the standard deviation. And since we are using this probabilistic analogy, the wave function kind of acts like a probability function. When we solve for the wave function, we are essentially finding where the object that the wave function describes is most likely to be at a specific point, or what our measurements are most likely to return, but we can never be 100% certain. Now, the wave function itself is not actually the probability. The probability at a certain time t that the object we want is between A and B, or in general, in some volume V, is defined by the integral over the volume V of the magnitude, well, it's actually the modulus, squared of the wave function over the entire volume. So this is the message of quantum mechanics, what we call Born's statistical interpretation. We never know exactly where an object is. Our measurements are always going to have some amount of standard deviation, and we can find that standard deviation by solving for the wave function through Schrodinger's equation. So now, one wave function alone is hard enough to study, but of course, through Schrodinger's equation, one object's wave function is of course going to influence the other object's wave function, and vice versa. So how do we keep track of that influence? Well, just like in classical mechanics, we want this joint wave function that describes both the state of psi 1 and psi 2 at any given point. But there is one critical distinction between classical and quantum mechanics. What is that distinction? In classical mechanics, you can take two seemingly identical objects. I'll actually take the different colored chalk. What? You can take two seemingly identical objects, and you say, well, I don't know which one is A and which one is B. If they swap places, I couldn't tell. Well, your natural response might be, well, mark one of them as A and another one is B. Or get a detective to follow them around. Or paint one blue and the other one orange. Or just tell them apart by where they are. One is on the left, one is on the right. And you might just say, well, the one that was just on the left has switched to the right, and the one that was just on the right has switched to the left. That is classical mechanics. In quantum mechanics, we can do no such thing. If we have two particles of exactly the same type, which means same spin, same position or wave function, same everything, we cannot tell them apart. They are, for all intents and purposes, totally indistinguishable. So think of it like this. Let's say I have a blue ball and a red ball. So I color one blue and I color the other red. And then I shuffle them around over and over and over again until eventually the orange one comes out on this side and the blue one comes out on that side. You will say, oh, obviously the one on the right would just move there when it used to be the one on the left. And obviously the one on the left was moved there. It used to be the one on the right. In quantum mechanics, now imagine that every single time you look at these things, they change color. So this one might turn from blue to orange one time you look at it. This one might turn from orange to blue. This one might be half orange and half blue, and you can't really tell which one it is. No matter the case, your observations fundamentally change the state of the system. So when you're left with an orange ball on the left and a blue ball on the right, you can't for sure tell me, well, this one used to be on the left, and that one used to be on the right. You don't know. That is the message of quantum mechanics, and that's what brings Bose statistics to life. See, now that means our joint wave function has to be symmetrical. Symmetrical means it will return the exact same result no matter if the blue ball was on the left or the red ball was on the right. It will return the exact same result if particle 1 is in state 1 and particle 2 is in state 2, as it would if particle 1 was in state 2 and if particle 2 was in state 1. That is what we want our joint wave function to do. But why? Why can't it be symmetrical? Well, think of it this way. Oh, thank you. If they weren't symmetrical, then every single time we measured something, we'd essentially be looking at two different versions of reality. Which one is determined by completely random chance. Doop, doop, doop. And not just that, since in the real world there were a lot more than two particles, we are looking at essentially infinitely many different versions of reality, and we don't exactly know which one is correct, because every time we make a measurement, we get a totally different result originating from one of them. Measurement becomes completely meaningless if our wave functions are anti-symmetrical. We have to make them symmetrical for the sake of making any measurement that we do meaningful. Otherwise, it's rubbish. So, when I say symmetrical, I don't exactly mean the wave function itself, but what actually defines reality. The wave function's modulus squared, which is the thing that we just saw in the probability density integral. This is what actually defines how reality and measurements look. So, that means it's all good if psi x1, x2 is equal to the negative of psi x2, x1. That is, it's okay if when we swap the order it becomes negative, because that gets washed off by the square. But everything else is not okay, which means we have two choices. Either this or that. Oh, sorry. Either this version of symmetry or that version of symmetry. And so, this version of symmetry goes to bosons. As you can see, they're named after S.N. Bose. Bosons. And this one goes to fermions, named after Enrico Fermi. So now, Well, we have the disjoint wave function is psi 1 x1, psi 2 x2, minus psi 2 x1, psi 1 x2. Sorry, I'm just a little bit scuffed. No, that's not right. Should be psi 1. It's one of those that doesn't compute. Plus. So the Pauli exclusion principle is important for fermions because the anti-symmetric rule applies to fermions. Their joint wave function is psi 1 x1, psi 2 x2 minus psi 2 x1, psi 1 x2. The Pauli exclusion principle states that two indivisible particles can't be in the same state. Why? Well, if they were in the same state, these would be equal. And so, if this becomes this becomes this, the wave function collapses to zero. And, for probability density reasons, wave functions shouldn't be zero. Specifically, we want the probability in the wave function to be somewhere to be equal to 100%, because it has to exist. So, that means we have the restriction that the integral from minus infinity to infinity, or over all of R3, if we're doing it in 3 dimensions, the wave function modulo squared has to be equal to 1. But if we put the wave function to 0, this is going to be 0. And no matter how complicated, multiply by and then it becomes 1. Which means if the two particles have 0 chance of being fixed on their space, they don't exist. This wave function doesn't exist. Which means that two particles that are fermions and are indistinguishable can't be in identical state. That is not true for bosons. When we have bosons, they're perfectly fine. Why is that? Well, the wave function is instead psi 1 x1, psi 2 x2, plus psi x1, psi 1 x2. So of course the psi 1 and psi 2 are the same, all it collapses to is this wave function. That doesn't exactly have to be 0, it can still exist. So we're fine. But that also makes a dangerous distinction between bosons and fermions. One, they both have to invent an entirely new kind of statistical mechanics to solve. So what does this all mean? Well, let's start with the very basics of statistical mechanics. Let's say we have n particles. This is our population. Then, these particles are going to be sorted into energy levels, because they have to have some amount of energy. And the whole message of quantum mechanics is that energy is in a continuous spectrum. It's discrete. There's a staircase of energy that every particle must go up. Well, it's more accurately described as a ladder, but whatever. So, let's say that these energy levels have some amount of what we call degeneracy. Now, degeneracy is usually a word applied to bad people, but degeneracy here does not mean what you think it means. It just means the number of possible states in one of these energy levels. So now, we can kind of imagine that the population is a bunch of balls, these are our bosons, and the degeneracy is a bunch of dividers. What we're going to do is when we split these guys up, into sections with these dividers, well, let's provide a simpler analogy. When we want to divide one whole amount between a certain number of things, and we want to see exactly how many ways there are to do that, what we do is we use something called the stars and bars method. We take all of the objects that we need to split up or separate. We might need to separate them between people at a lunch table, or we might need to separate them between energy levels. So, what we have is all of our particles that we need to divide up, and let's say we need to divide them up between 3 groups. Then, we can put 2 little walls in place. Anything to the left of this wall goes to group 1. Anything to the right of this wall goes to group 3. Anything in the middle goes to group 2. Of course, you can generalize this to any amount of walls you like. So, of course, there's always going to be n-1 walls, or what this method calls bars. Now, we take these walls and we put them somewhere between the balls. Now, this amount goes to group 1, this goes to group 2, this goes to group 3, and this goes to group 4. And that can, of course, be generalized. Now, how many ways are there to do this? Well, this is just a standard combinatorial problem. You have 5 indistinct objects, 3 indistinct objects, and those 2 types of objects are distinguishable from one another because, you know, the stars and the bars aren't the exact same thing. So all you have is the total number of stars and bars divided by the number of stars and the number of bars. Well, it's not that simple. More like the total number of arrangements of the stars and bars, if they were all distinguishable, divided by the number of arrangements of the stars, because they're indistinguishable, and the number of arrangements of the bars, because they're also indistinguishable from one another. So, in this case, how does that manifest? Well, here's what we're doing. In quantum mechanics, as I've said earlier, we don't know exactly how reality looks like at one point in time. All we can really calculate are probabilities. So, when we find the probability of a state occurring, some complicated things have to happen. As I've said earlier, particles aren't distinguishable. So let's say you're flipping 2 coins. One of these coins can land on heads or tails, and the other could also land on heads and tails. Now, of course, there were 4 possible results of this test. You get both heads, you get both tails, you get a head and a tail, and a tail and a head. This is the common example of macro and micro states. Here, we have 2 heads and 0 tails. Here, we have 2 tails and 0 heads. And for both of these, we have 1 head and 1 tail each. Here's the thing. While we can distinguish between these theoretically, when we're doing the math for probability, we know these are 2 separate possibilities that could happen. Experimentally, we have absolutely no idea when we read the measurement that it's 1 head and 1 tail, whether the head came first or whether the tail came first. And so, that's essentially how quantum particles act as well. you have the 2 heads, 0 tails possibility, the 0 heads, 2 tails possibility, and the 1 head, 1 tail possibility. And common sense would say, well, all 3 possibilities have the same probability. But here's the thing. These are all the macro states. These are all of the states that we can tell the difference from experimentally. But we know that there are things we can't tell the difference from theoretically. We know that the HT outcome and the TH outcome both exist and both have equal probability to these, but we can't tell the difference between these two. These are what we call microstates. We can know about them theoretically, but they can never be told apart experimentally. So that combines to make one macro state, which, because it encompasses more microstates within it than the other two, which only encompass one microstate, these two have probability 1/4, and this has probability 2/4, or 1/2. So that is the big message behind statistical mechanics. This is basically what we have to do now. What we're going to do now is say that, well, every microstate has the same probability, which means that to find the most probable macrostate, or the most probable state of reality that we can actually experimentally detect, we need to find the macrostate that has the most microstates inside it. How do we do that? Well, what we're going to do is take all of our population, Ni, and the degeneracy level of our energy level, Gi, and just repeat the formula that I wrote down on the board earlier. And now, this is going to be the number of microstates for macrostate number I. What we want to do is maximize this. Find the I that makes this super duper big. Now, to do that, we want to use an approximation, because factorials are absurdly difficult to work with. What approximation do we use? Well, in the 1700s, a little-known mathematician named Abraham de Moivre came up with a nice and simple way to approximate the factorial. What he did was he took the logarithm of the factorial. See, as you know, the logarithm of a times b is just the logarithm of a plus the logarithm of b. And a factorial is the product of all integers up until a certain end. So, for example, this is 5 factorial, and it would just get split into the sum from n equals 1 to 5 of log n. What de Moivre did is he took this sum and approximated it using an integral instead. He instead took the integral from 1 to 5 of log n, which is, well, it's not very accurate when n is maxed out at 5, but when this is very large, it becomes surprisingly good. And so, what does this give us at the end of the day? Well, it gives us n log n minus n. Well, the minus n is a side effect of this. So, if we get this result out of that integral, what can we say? Well, now we know, erasing this, that the logarithm of the factorial is approximately that. Another advantage that's on our side is that the logarithm is purely an increasing function. There is no point where the input can increase and the actual logarithm decreases. Which means that if we maximize the logarithm, we are maximizing the actual number. So let's just take the logarithm of this. Sorry. So that means the log of ti is equal to, well, the log of a over b is equal to the log of one subtracted from the log of the other. And now we can just plug in what we already know about the logarithm of the factorial. This becomes, well, ni plus gi factorial, that's approximated by, oh, I don't know why I wrote an equal sign here. This would be an approximation sign. Ni plus gi log ni plus gi minus ni minus gi. And then expanding these other two, we get plus ni log ni, minus ni log ni plus ni minus gi log gi plus gi. And now what we can do is just cancel these out, and we're left with the, oh, I left the eraser on the floor. We're left with a relatively accurate estimation that log ti has to be equal to ni plus gi log, well, factorizing it even better, ni log ni plus gi over ni plus gi log ni plus gi over gi. Now, if we want to maximize this, well, first we have to place a more specific condition. We can't do anything right now. But here's the thing. While we can't tell two quantum particles apart, at least we know that they will never change in number. If we are particles, we know a third will never suddenly pop into existence, and we know the second will never suddenly disappear. That cannot happen. Which means we can at least rest assured with one thing. The sum of ni will always be equal to some number, the same number. And we can actually be sure of another thing. The sum of epsilon I and I has to be equal to a consistent potential energy. The energy cannot just come out of nowhere, and it cannot just leave out of nowhere. That's a no-go. So, once we take those thermodynamical laws into consideration, well, what we can do is say that means the change with respect to ni is going to be 0 here. The change with respect to ni is going to be 0 here. And now, if we take the change in ti with respect to ni, log dti is equal to log dni plus gi. Hold on a minute. No, that's not right. I have to re-expand this. This becomes ni log ni plus gi minus ni log ni plus gi log ni plus gi minus gi log gi. Of course, if we take the derivative with respect to ni, that is going to disappear. This is going to, well, approximately disappear, and we're essentially left with the remains of this. We get dni log ni plus gi minus dni log ni. And now, what we're going to do is we're going to apply the method of Lagrange multipliers. Now, I think I'm just going to keep this short now. Yeah. No, I'm fine. All we get is that once we apply the Lagrange multiplier, which is essentially a restriction that comes from these two, what we get is that ni has to satisfy something very specific about gi. Has to satisfy that it is gi over, I believe, epsilon I to some power minus 1. Oh, wait a minute. It should be minus alpha minus beta. No, wait a minute. Oh, yeah. We get this. Now, the important part of that is that Fermion's equation, meanwhile, looks a little bit more like this. And the only difference is that a sign switches. But that actually makes a world of difference. See, with this, Bose was able to predict something unimaginable. Uh-oh. When there's a plus 1 in the denominator, then the denominator is totally bounded. No matter what the other term is, it's always going to be positive, since the degeneracy can never be negative. And so, that means this denominator is always going to be at least 1. So, what we're going to get is that ni is at least gi. Of course, that is not true here. With this minus 1, we can make gi, or this denominator, in total, as low as we like. We can make gi minus alpha minus beta epsilon approach 1. And so this denominator approach 0, and this whole thing approach infinity. And that is how Bose predicted the Bose-Einstein condensate. Levels implies that you can put an unlimited number of particles up to a macroscopic scale into one state. And for convenience purposes, yeah. Yeah. Hmm? Hmm? Oh yes, I'm so sorry. But still, particles have to stay in the ground state. And if a macroscopic amount of particles stay in the ground state, which is something that can be observed using classical equipment, that would essentially confirm that all of Bose statistics was correct, and also essentially invent a new state of matter. For how particles act in the ground state is not how they're normally supposed to act. Now, of course, in 1925, when Bose predicted all this, there was absolutely no experimental equipment that could confirm this, and so no hope of knowing this was true. And unfortunately, it would take more than 70 years, by which Bose's death had already passed, until 1995, when 3 scientists at, I believe, Cornell University showed that a Bose-Einstein condensate actually did exist with experimental equipment. And in 2001, those 3 won the Nobel Prize that Bose himself should have gotten for the discovery of the Bose-Einstein condensate. That's it for today. Thanks everyone for watching. Oh, wait. Thanks everyone for listening, and we'll see you in the next one.
Hello.
Yeah, sure. I can take questions.
আচ্ছা, যারা কোশ্চেন করেছেন ও এখানে আসবে, এই মঞ্চে এসে এখান থেকে উত্তর দেবে, এইখানে চলে আসবে আপনাদের মধ্যে।
It's a little bit crowded.
আমি ডক্টর শুভদীপ শর্মা এবং ডক্টর শ্যাম দাসকে আমি ডাকছি। ঠিক আছে, ওকে 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 ওকে। আমি ডক্টর শ্যাম দাস এবং ডক্টর শুভদীপ শর্মাকে মঞ্চে ডাকছি।
Oh my goodness. Oh, that was a bad idea.
নেমে গেছে? ও ওকে ওকে ওকে। হ্যাঁ, এই শ্যাম দাস, শ্যাম, এই আর একটা কই মাইক্রোফোন ওখানে আছে।
Well, how can I answer the questions without the board?
হ্যাঁ, কিন্তু অঙ্কে শোনেন না, অঙ্কের কিছু আছে সেটা ওইখানে ডিরাইভ করতে পারবে না তো। হ্যাঁ, কিছু ডেরিভেশন আছে এখানে পারবে না। হ্যাঁ, ওখানেই ভালো স্টেজে নাম্বার থিওরি। হ্যাঁ নাম্বার থিওরিটা হি নিডস বুক। হ্যাঁ, হি নিডস বুক। I think it will complete the session. Okay, তাহলে যারা কোশ্চেন করবে তাদেরকে একটু এখানে রাখেন।
Oh, okay.
আচ্ছা, আমরা এখানে প্রচুর কোশ্চেন পেয়েছি এবং তার মধ্যে অনেকে নিজের নামটা লেখেনি। আমরা চাইবো যে কোশ্চেনটা করেছে, একটা যেহেতু ইন্টারাক্টিভ সেশন, সেই স্টেজে আসবে, সরাসরি প্রফেসর বাড়িকে কোশ্চেনটা করবে, তাহলে ইন্টারাকশনটা হবে আরও সুবিধা হবে। তো যেগুলো অ্যাটলিস্ট নাম দেওয়া আছে আমরা তাদের নামে ডাকবো, তারা এখানে আসবে। আমি
হ্যালো, উপরে হলে উপরে করলে হ্যাঁ উপরে।
Okay.
This is to inform to you all, the question answer session will be followed by lecture sessions on number theory. Okay.
Dr. Shyam Das? Yes.
Sure.
Please, Dr. Subhadeep Sharma. Okay, question. Number 3.
So now we will have session on number theory. Professor Bari will deliver the session on number theory, and then we will go to the question answer session, both based on physics as well as number theory. Okay. And any questions? Any curiosity on science related, any further topics?
Candidate কে দাঁড়াতে হবে, candidate কে
Okay. So I've been told to give a lecture about number theory as well. Now, unfortunately, the number theory lecture has been prepared for the University of Gorbanga, so I don't want to spoil the surprise to them, but unfortunately I also have to give in to your demands. So I'll talk a very little bit about number theory, and specifically the section of number theory that I research in. So, what I research is a problem surrounding the Riemann zeta function, but not the Riemann hypothesis. That's a little bit too hard for me to approach, considering my current mathematical background. Probably too hard for any human on the earth to approach. Instead, what I'm discussing is a totally different problem, which you might be familiar with through the title of the basal problem. We know that 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc. converges. This is just a P series. And of course, P is equal to 2, which is greater than 1. So it converges. But the question is, what does it converge to? And some of you probably recall that the answer is 1/6 of pi squared. Now, this can be proved in a variety of ways. In fact, you can extend this proof to what happens if you take the 4th power. This time, you get 1 over 90 multiplied by pi to the 4th power. In fact, you can actually extend this to any even number. Well, any even positive integer. And you will get a result that is pi to the 2n multiplied by the 2nth Bernoulli number divided by, I believe, 2n factorial. But don't quote me on that one. That's probably wrong. And this has been known since the 18th century with Euler. But there's a different problem. The odd numbers were expected initially to be very, very similar, with some rational coefficient multiplied by pi to said odd power. But that didn't show its face. In fact, studies showed that if zeta 3 was a rational multiple of pi cubed, then A and B would both have to be extremely large, which is of course uncharacteristic when the previous denominators of zeta 2 and zeta 4 were 1 in 6 and 1 in 90, which meant that zeta 3 probably wasn't a rational multiple of pi cubed. And in fact, to this day, we still don't have a closed form for zeta 3. Just very recently, well, not actually very recently, before most of us in this room, including me, was born, in 1979, it was proved, that's mathematically pretty recent, that zeta 3 was irrational. Through a lot of complicated techniques that I don't want to spend the time today elaborating on. But the question is, of course, what about the higher odd numbers? This technique, unlike Euler's, did not generalize to 5. Zeta 5 is probably not a rational multiple of pi to the 5 either. In fact, we don't even know whether it's irrational, although most mathematicians strongly speculate that it is. In fact, in general, we don't know pretty much anything about the irrationality of these odd numbers. And of course, that is the problem that stood for over 300 years, that even the greatest minds of mathematics cannot solve, and a problem which my research is tangentially related to. So I hope this interests you, and maybe you can take a Google search about it, and maybe even get interested in it yourself. Yeah, that's about it for number theory. Thank you.
ওদেরকে ডেকে নিন নামগুলো
I will sit. I will sit. Sure.
তাহলে আমরা এবার ইন্টারাকশন সেকশনটা শুরু করছি। আমি কয়েকটা নাম ডেকে নিচ্ছি, সুবিধা হবে, তাড়াতাড়ি হবে। সৌনমিকা সাহা, যাদের নাম ডাকছি তারা এই মঞ্চের ডান দিকে আসবে। সৌনমিকা সাহা, অদ্রিজা দাস, ডক্টর শুভদীপ শর্মা অলরেডি আছে, নৌসিন রহমান, দেবলীনা মধু ফ্রম সিসি গার্লস, অনুষ্কা হালদার। যাদের নাম ডাকছি তারা মঞ্চের ডান দিকে এসো। হ্যাঁ, সৌনমিকা সাহা আছে, তাড়াতাড়ি আসবে। এই প্রশ্নটা আমরা প্রথমেই, তোমার নাম?
সৌনমিকা সাহা।
হ্যাঁ, এইটা আজকে টপিকেরই রিলেটেড, সেই জন্য এই কোশ্চেনটা করেছে। ধরো, তুমি বলো।
Okay.
Good afternoon, everyone present here. I am Shonamika Shaha from Usha Martin School. I study in 11th, and today my question to our little Einstein is, if we could engineer a stable Bose-Einstein condensate of photons, what futuristic technologies might be possible? This is a...
That's a question I don't have the capability to answer. I don't want to disappoint you, but I mean, I would rather admit a shortcoming than spread false information. I'm sure there's someone out there that can answer this question, but not me. I'm not good enough at quantum mechanics.
Oh, it's all right. It's all right.
Sorry.
Thank you, thank you.
Thank you. It's over there. I'll erase the board if you want.
কোশ্চেন যেন ম্যাথস ওরিয়েন্টেড উনি চাইছেন। হ্যাঁ।
Is that a homework question?
নিউমেরিক্যাল প্রবলেমস যারা স্কুল স্টুডেন্টস আছো তারা নিউমেরিক্যাল প্রবলেমসও দিতে পারো।
So consider Sn to be a sequence whose nth term is given by this expression.
Oh, wait,
Can you throw some light on the supremum of Sn?
Wait, wait. Oh, I see what you mean. Okay. Okay, I have to think about this for just a second. So, what I'm going to do is just give a heuristic approximation, and hopefully from that, why am I holding the microphone? I don't need two at once. Hopefully from that, we can get an idea of what the supremum is going to be. So, first of all, there are going to be n terms in this summation. So we want to consider what happens when n gets very large, right? We want to consider what happens when this approaches the limit of infinity. Now, when that happens, when this approaches the limit of infinity, well, let me put a bound on this. This is, of course, wow, this is actually tricky. First, let me see what happens if I just write out n equals 2. We get something like this. Oh, no, that's not how math works. We get 2 over k squared plus 2k plus 4, which can definitely be separated by partial fractions. So this, hey, wait a minute. I'm just going to rearrange this to k squared plus nk plus n squared quickly. And now what I'm going to do is refactor that as a quadratic. So I'm going to see if I can split this into k minus a times k minus b or something like that, and then use partial fractions. So what we get here is a is equal, so let's see, minus b plus minus the square root of b squared minus 4a, which is 1 times c, which in this case is n squared. Hey, wait a minute. So we're going to get, this does not have a proper root. It's all going to be imaginary, or sorry, complex, which means, okay, this is going to be a little bit more difficult. All right. So let's see. First of all, are these terms increasing? Well, we get 2 over k squared plus 2k plus 4, which means the first term is just going to be, well, no, it's going to be decreasing. Because the denominator is always an increasing function, it's a quadratic, that means the terms of this are always going to be decreasing. If the terms of this are going to be decreasing, that means that this is bounded very weakly by n multiplied by its first term, which is just n over 1 plus n squared. So if this is always less than or equal to n times n over 1 plus n squared, and of course that's equal to n squared over 1 plus n squared, and that approaches 1 as n approaches infinity, I am going to wager that this is equal to 1. And just to test, just as a sanity check, I'm going to take the case for n equals 2, 2 over k squared plus 2k plus 4. That's going to become 2 over 1 plus 2 plus 4, or 2 over 7, plus 2 over 4 plus 4 plus 4, which is plus 2 over 12, or 1 over 6. And of course, that's just equal to 12 plus 7 over 42. Yeah, so I believe this is equal to 1. And if not, it's at least less than or equal to 1. Okay. Actually, it is probably lower than that, but let me think. This is a very weak upper bound. Can I tighten it a little bit? What happens if I do? Well, okay. The first term is the greatest, but do all other terms disappear as n becomes very, very large? The first term is always going to be n over 1 plus n squared. And the second term is always going to be n over 4 plus 2n plus n squared. Now what that means is that actually, proportionally, as n approaches infinity, these two are basically the same. Since the coefficient of n squared never changes, yeah, it is going to be 1. So I think that is my final conclusion. Yes. So essentially, here's how I went about it. If you take k equals 1 to n of n over k squared plus nk plus n squared, you first of all realize that since, this is an... Since this is an increasing function with respect to k, as k goes up, this denominator is going to go up, and so the terms are going to go down. Which means that, at the very least, the first term is always going to be the greatest. And if the first term is the greatest, this is always less than or equal to n multiplied by the first term. And the first term is just n over 1 plus n squared. So then you get n squared over 1 plus n squared, whose supremum is equal to 1. But of course, that's not a proof that this supremum is equal to 1. This is just a proof that it's less than or equal to 1. Well, less than or equal to. So, what made me come to the conclusion that it was exactly 1 and not just less than or equal to 1 was that if you write out the terms, this is n over 1 plus n squared plus n over 4 plus 2n plus n squared plus n over 9 plus 6n plus n squared. 6. And so on and so forth. But, hold on.
You're taking the summation. A equal to 1.
Yes. And so on and so forth. And the thing I noticed was that if you ignore everything except the highest degree term, which is going to be the only term that matters in the limit that n approaches infinity, then you get that, well, this is going to approach the same thing. So as n approaches infinity, these terms are all going to approach 1 over n, as these terms are going to shrink a lot with respect to n squared. This is going to approach 1 over n. This is also going to approach 1 over n. And so on and so forth. And of course, when you repeat 1 over n times, you're just going to get 1. So that's how I came to the conclusion that it was 1. But there might be a flaw.
Are you taking the divergence?
Well, I don't think this is exactly the same as the harmonic series given... Hold on a minute. No, it's fine. I'm just thinking for a second. Maybe it really is similar to the harmonic series, and I'm missing something. But oh well, we can move to the next question if you want. Sure.
Next question now.
Good afternoon, sir. I am Audrija Das from Usha Martin School, and today I want to ask you, what's one failure or tough moment you had, and how did you push through it?
I guess I have failed a lot of times in life, but I mean, tough moment. Okay, I mean, that is a hard question. It's one that I get very often, and yet one that I forget the answer to so often. But I would say that, I mean, I just persevere through math because I view it as something that I enjoy, not exactly as like a chore that I'm made to do all of the time. Of course, when it comes to other school subjects, I'm like most of you. I really, really hate failure, and of course, sometimes I can't stop myself from failing anyway, but I don't see it as necessarily fun. I kind of see it as a chore. But mathematics in particular, I've never stopped doing it even when I fail, because sometimes it doesn't even really feel like work. The act or process of discovery itself is like really fascinating. It's almost like getting dopamine wired up to your brain, and you get it instantly whenever you figure something out. That's just something that's always stuck with me, and I think if you can turn math or whatever subject you like into a passion for you as well, where you always love every new discovery instead of feeling like you're being made to do it by an outer force, then you can also push through anything as well. But of course, if you hate a lot of subjects, like I do, sometimes you'll feel like you just want to give up. And then, in those cases, I just give up and I try again later. Because giving up and then trying again and then giving up and so on and so forth only makes your next attempts worse. So yeah, that's generally my advice. For your most loved topic, make it a passion instead of something that you feel like someone else is forcing you to do. And for everything else, just give up and try again later.
Okay, sir. Thank you, sir.
Yeah, no problem.
ওকে এক মিনিট আমি আরও কয়েকটা নাম ডেকে নিচ্ছি তাড়াতাড়ি হবে কেশব চন্দ্র রয় টিচার
Good afternoon, sir.
প্রত্যুষ সাহা ভার্গব দাস মোহাম্মদ রিফাক আলী জাসমিন আহিদা নিশা আর প্রিয়াংশী দাস যাদের নাম ডাকলাম তারা একটু এই স্টেজের পাশে চলে আসবে এক্ষুনি হ্যাঁ নেক্সট
Good afternoon, sir. I am Noshin Rahman from St. Mary's School, and my question to you would be, if light can behave like both a wave and a particle, what does that tell us about the nature of matter? Is every substance dual in nature, or is light an exception?
Actually, this is kind of what physicists were thinking in the 1940s. So the problem was, light is still considered a wave for most purposes, but in one specific experiment, the double slit experiment, it was shown to behave like a particle. In that, it gave the same interference patterns as a particle would. Not as, oh wait, no, sorry, it's the opposite. Light was deemed a particle at that point, but it gave off the interference pattern that a wave would. And so the problem was that even though light was supposed to be a particle, it was displaying qualities expected of a wave. And so people started questioning if it was either a wave or a particle, and eventually we decided, well, it was a particle, but any particle can always show qualities of waves. So essentially, there was a physicist named Louis de Broglie, and what he showed was that every particle can essentially be described by a wave with very, very, very high wavelength. And of course, when you zoom in very far, you can when you zoom in very far, you can see that essentially on a lower level, every particle kind of is a wave. So in some sense, you can say everything is a wave, but some waves are more wavy than others. It's a very strange question that people have been exploring for the past 100 years. Yeah, no problem.
Good afternoon, sir. Devrina Madhu, today I want to asking you that a number is randomly selected from the set of all numbers x where 7 by 8 greater than equal to x greater than equal to 4 by 3. What is the probability that the number will be greater than or equal to?
You guys gotta stop giving me your homework questions. Nah, just kidding. Oh, 4/3. Okay. 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 So let's see. Hey, wait, this really is kind of simple. Okay, so what we're assuming here is that essentially what we call a uniform distribution is being selected from 7/8 to 4/3. That is, kind of every number has an equal probability of being picked, in a sense. And so now, you are being asked, what's the chance that the number is greater than 1? It probably looks something closer to this, but whatever. And that probability is just the length of the interval from 1 to 4/3 divided by the length of the interval from 7/8 to 4/3. And of course, the length of the interval from 1 to 4/3 is 1/3, and the length of the interval from 7/8 to 4/3 is 4/3 minus 7/8. So that's just going to be 32 over 24 minus 21 over 24, which is also equal to 11 over 24. And so that's 1/3 times 24 over 11, which is just an 8 over 11 chance. Thank you. Do you want to take your question paper? No problem.
Good afternoon, Professor. Myself, Anushka Haldar. I'm from North Point English Academy, and my question to you is, why is time considered to be 4-dimensional?
Well, it's a little bit more complicated than that, essentially. In some areas of physics, we don't consider time itself to be 4-dimensional. We consider it to be another dimension alongside the already considered dimensions of space. And that's because okay, sure, I'll write on this side. When we're talking about relativity, you can move to this side if you want. When we talk about relativity, in classical mechanics, we have this thing called reference frames, where, from one person's perspective, some things, like position, are going to be different in that person's perspective than from another person's perspective. For example, I might say that that audience member is 10 meters away from me, but the person sitting next to him might say that that audience member is only 1 meter away from him. So, in this place, distance is not conserved. However, in classical mechanics, we can all agree on what the time is. So time is conserved no matter what reference frame you're in, i.e. who you ask. But the problem is, in relativity, time is not conserved, and neither is distance. What is actually conserved is the speed of light. Or, to put it in distance terms, what we call the space-time invariant. And, of course, since time is one of the quantities that is no longer conserved, people decided to lump it in with the quantities that we already knew were not conserved, distance. And so now, neither time nor distance are conserved, which is why we essentially consider time another dimension, just like the x, y, and z dimension. So that's why we consider space and time to be 4 dimensions together, instead of just space being 3-dimensional and time being a separate object.
I have another question. Is mathematics something we invented or something we discovered?
Oh, that's the big philosophical question. I'm going to say something, well, it depends on which area of mathematics. Like the basic areas of mathematics, I would say, are discovered, but some parts of mathematics, including some tools we made to view other parts of mathematics, are definitely invented. So I think it's kind of a mix of the two. But depending on who you ask, including other mathematicians, you'll get a range of other answers.
Thank you.
No problem.
Good afternoon, Professor. I am Bhargav Das, and I am also from North Point English Academy. And today my question is one of the Ramanujan's modular equations, and you just have a look of it.
Oh boy. Okay, that's going to be a little bit difficult. Okay, so we are being asked to prove P is 16 times alpha times 1 minus alpha, beta times 1 minus beta to the 1/8. Meanwhile, Q is beta times 1 minus beta over alpha times 1 minus alpha to the 1/4. Hey, wait a minute, is this another homework question? So we have to prove Q plus 1 over Q plus 2 root 2 P minus 1 over P is equal to 0. So how do we do that? Well, I propose first we substitute alpha times 1 minus alpha is x and beta times 1 minus beta is y. That would certainly make things a lot simpler, unless there's some restriction between alpha and beta that's not specified, but I don't see it on the paper here. So we get P is equal to 16xy to the 1/8, and Q is equal to y over x to the 1/4. And now all we need to do is prove this. And how do we do that? Well, I'm just going to rearrange it to Q plus 1 over Q is equal to 2 root 2 1 over P minus P. And now, well, this side is, oh, wait a minute, this might be a little bit harder than I thought. Y over x to the 1/4 plus x over y to the 1/4. And this side, meanwhile, is, am I missing anything? No. 2 root 2 times, okay, what I'm going to do is say 16 to the 1/8. Well, 16 is just 2 to the 4th, so this can essentially be written as the square root of 2 times everything else to the 1/8. So this can be written as 2 root 2, since P is essentially the square root of 2 times that, it's going to be the square root of 1 over the square root of 2 times xy to the minus 1/8 minus P, which is the square root of 2 times xy to the 1/8. So now we have to prove this side is equal to that side. But how would we do that exactly? Well, first I'm going to distribute this constant, and we get 2 minus 4 in here. And then the second thing I'm going to do is multiply both sides by xy to the 1/4. That's going to remove all of the fractions here and make this into x to the 1/4, y to the, hold on, 1/8, no, 1/2, plus y to the 1/4, x, y to the 1/2, plus x to the 1/2, is equal to 2xy to the 1/8 minus 4xy to the 3/8. So now we get this, and now I'm just going to, let's substitute in x to the 1/8 is equal to A, and y to the 1/8 is equal to B. So now, all I'm getting from this is 2 to the 2ab minus 4a cubed b cubed is equal to a to the 4th plus b to the 4th. Oh, wait a minute. So this is, it's a quadratic equation. Plus 4a cubed b cubed minus 2ab is equal to 0. And, hold on a minute. That doesn't sound true in general if we don't have restrictions. So what happens if I just said, A is equal to 1 and B is equal to 1? Or am I wrong? Hold on. Oh, no, that obviously works. Yeah, that doesn't seem right. Like, that sounds extremely fishy, if you get what I'm saying. So, let me just test it very quickly. 16 plus 1 plus 4 times 8 times 1 minus 2 times 2. Yeah, 17 plus 32 minus 2. That's not equal to 0. So, yeah, it looks like there has to be another restriction between P and Q. Because, let me just work back to see if I can find, so y is b to the 8. Are alpha and beta supposed to be integers?
It's actually not said in the question, like if alpha and beta are integers, but you can just assume that they're integers and work on it, and if you get some clue that will be very beneficial.
Yeah, because this doesn't seem true in general if they're integers, but I might be missing something. I might be missing some context. So that would imply x is equal to, 1 and y is equal to 2 to the 8. I forgot what that is. I'm pretty sure it's 1024, 512, 256. And so, oh, wait, that's the peculiarity. Wait, is 1, oh yeah, that's possible. That's definitely possible. So, if alpha is just the golden ratio, and beta is whatever the solution to beta's, let me see, beta times beta minus 1 equal to minus 256. So beta squared minus beta plus 256 is equal to 0. Yeah, something is a little bit fishy here. But I'm going to keep going just to see if there really is a proof. Because it seems fascinating, but it also seems very wrong. 2a squared b squared minus 1. And yeah, that doesn't seem correct. I might be making a mistake here, but that doesn't seem like it should be true. So let me just see if there's a solution to this, and that confirms that this isn't true in general. So then we get minus b plus minus the square root of b squared minus, oh wait, no. Oh, there were conditions.
Not a question in Q. I think we should move to the next question.
Are you sure? Can you give me 5 more minutes or 2 more minutes?
2 minutes is sufficient.
Okay, 2 minutes is fine then. So I'm just going to rewrite this one more time by saying we want to instead prove pq squared plus p plus 2 root 2 p squared q minus q is equal to 0. I multiplied both sides by pq here. And now, is this even true? Well, p is equal to, I'm going to say, yeah, let's say a is equal to alpha times 1 minus alpha to the 1/8, and b is equal to beta times 1 minus beta to the 1/8. Then, that way, we know that p is equal to the square root of 2 ab, and q is equal to, b squared over a squared. So with that said, can we show that b squared over a squared plus a squared over b squared plus 2 square root of 2 p, which is the square root of 2 ab, minus the 1 over the square root of 2 ab is equal to 0. Yeah, that sounds extremely false, but I don't know. I can't trust it. So at the end of the day, we get this, and I'm going to see one more time if we can make a common denominator here. So we get a squared b squared, 2a squared b squared over, no, that's not how things work. We get b to the 4th plus a to the 4th over a squared b squared minus 2ab plus 4ab. Yeah, so we once again get this question. And, you know, I firmly believe that that is not true in general. A cubed, b cubed is equal to 0. So, I'm just saying, oh, wait a minute, alpha and beta can only be between 0 and 1. That was obvious from the start. So A and B can only be between 0 and 1. But even still, that doesn't sound totally true. Like, just to do one more sanity check. 2n to the 4 plus 4 and, wait, no. Yeah, plus 4n to the 6 minus 2n squared. Yeah, okay. So, in the very simple case that alpha is equal to beta, over here you seem to get 2n to the 4th, say if alpha is equal to beta, a is equal to b, 2n to the 4th minus 2n squared plus 4n to the 6th is equal to 0. And that's simplifying to 2n squared minus 2 plus 4n to the 4 is equal to 0. Or, you know, if you substitute in something for n squared, you get 4x squared plus 2x minus 2 is equal to 0. And of course, this equation has 2 roots at most, but there are infinitely many values between 0 and 1 that don't satisfy this equation. So of course, we've reduced it to a quadratic equation being equal to 0, which isn't true in general. So I'm going to say that this heavily depends on the values of P and Q.
Okay, sir. Thank you.
No problem.
Hello. Good afternoon, Junior Einstein, Subarna Bari sir. My question from Senior Einstein, Grand Unified Theory, 4 fundamental forces, electromagnetic wave, electric force, gravitational force, weak interaction, strong interaction. He predict 4 forces come from same source. Now 3 forces prove from one source. Your opinion about Einstein predict? 4 forces come from same source.
Wait, am I being...
Not proved yet.
Wait, am I being asked to provide a grand unified field theory?
Yes.
I can't do that. I mean, I can't get a grand unified field theory. Even the best physicists on the planet can't get it with years and years of work. So, I mean, I can't come up with it on the spot. I would heavily hesitate to even call myself a junior Einstein. So, you know, I can't answer every question about physics.
Another question. Einstein get Nobel Prize in relativity, photoelectric effect, another invention. Are you feel he took another Nobel Prize in photoelectric effect? Photoelectric effect.
Wait, are you asking me if Einstein had another Nobel Prize, what would he get it for? Probably his work on Brownian motion, because that was very significant, but his work on quantum mechanics, especially with Bose, was also very significant. So if something would have to win him the Nobel Prize, again, it would be one of those.
Thank you.
No problem.
Good afternoon, Professor.
Good afternoon.
I am MD Rifa Kali of Class 8 from St. Mary's School, Mala. My question is, how can we get super solid state of light?
Oh wait, let me see here. A super solid speed of light? Oh, state of light. Yeah, I think that's a tricky phenomenon because light in itself, see, the thing with solids is we define them to essentially have this sort of crystalline structure, where the particles or atoms inside are strongly bonded with one another and will not rigidly change their shape. And the problem with photons is that unlike regular atoms or even electrons, they are not known to form those atomic bonds with one another. Those require very specific quantum properties that light simply does not have. So there's no temperature you can cool light down to that will make it act like a solid, a liquid, or even a gas. Light kind of does its own thing. And so if it can't be made into any of these three states of matter, I would heavily doubt that it can be made into a supersolid.
Thank you for that.
No problem.
A very good afternoon everyone here. Myself Prof. Shah. I am here on behalf of Holy Child English Academy. My question for you today is, do you think creativity is as important as intelligence in the field of science?
Yeah.
Please justify your answer.
Yeah, I think it's definitely a little bit more important, in fact. With creativity, even if you don't have the intelligence to carry things out and do all of the calculations to their completion, then I think that creativity will get you far itself. And in fact, I think creativity for some people would be defined as part of intelligence, as creative intelligence. So I think the answer to that question really depends on what you define intelligence as. But if you define it as a separate object from creativity, I would say creativity is a lot more important.
I refer intelligence as academic intelligence.
Calculative intelligence. Well, we all know of Michael Faraday. He never received any formal education from many people, and so he had almost no intelligence on how to write equations down or calculate things. And yet still, we credit so many laws to him because of his pure creativity that was able to get him through becoming one of the geniuses that we know today in math and physics, despite not even writing down his own law of induction.
Do you think the power of creativity can overcome the power of intelligence?
Yes.
Why?
I think that intelligence, well, without creativity, well, it can only refine existing ideas, but it can never come up with a new one. And I think coming up with new ideas that can outperform even the most refined version of the old ones is what humanity is all about, and it's what got us this far. The light bulb would never have been invented if people just kept making the candle better and better. You need a new idea to come by in order to make really significant improvements.
Thank you.
No problem.
Good afternoon, sir, and everyone present over here in person. Myself, Priyanshi Das, and I'm from Sister Nivedita Public School. And my question to you today is, can gravity and quantum physics be united into a single coherent theory? And if the answer is yes, then how?
Well, that is a very hot question that a lot of physicists today are trying to solve, to put it lightly. I'm being asked here, I think, a lot of questions that are still unsolved and will probably be unsolved when I die. So, you know, quantum physics and gravity can probably be put together, but I mean, nobody knows how, and I definitely don't.
Thank you, sir.
No problem. No problem.
Good afternoon, sir. I am Jasmine Adanisa from Balagals High School. My question is, do you believe in multiverse?
In the multiverse? Well, yeah, it sounds plausible, and I mean, it could exist, but I have no scientific reason to really believe in it, but just the thought of it alone sounds nice. So in the absence of any scientific evidence against it, and no scientific evidence for it, I'm still going to say I believe in it, because it would be cool.
Sir, can you solve either one of those?
How many dimensions are there? How do you explain dimensions? Oh, wait. That is an extremely large number that it would take writing on everybody's skin here and the entire room just to write out. That's the definition of the zeta function. And is there anything else here? Will we ever be able to reach a universe not even hour? These are some interesting questions. It's fine. It's always good to ask questions, even if you think,
Hello, good afternoon everyone.
Very good afternoon to Professor Bari. I have a question that in quantum entanglement, when we have two correlated particles, then if the state of one particle changes, then there will be instantaneous change of the other's particle state. So does it violate the special theory of relativity?
Actually, yes. This is what was called the EPR paradox. So the E there stands for Einstein, because along with two other physicists, he thought coming up with this would totally dismantle quantum mechanics. Essentially, the Pauli exclusion principle states that two fermions cannot have the exact same state if they're indistinguishable. So if one has state up, the other must have state down. And so Einstein argued, as you said, if you measure one particle, then you instantaneously know the other particle state without measuring it at all. And so that doesn't make sense. The information has reached you twice as fast as the speed of light, which can't be possible. So if the information is reaching you at twice the speed of light, then that violates relativity, which we already knew to be correct. And so Einstein thought, well, quantum mechanics is dead. But entanglement is a little bit special, because essentially all it says is that now both particle states depend on each other in the most fundamental way. You literally cannot know the state of a single one before knowing the state of both. That is, the wave function cannot be factored into separate components that will individually tell you about psi1 without knowing about the other particle state. You have to know both. This is just rudimentary. This is not what a wave function actually looks like. But you have to know both particle state in order, you have to know both particle state to know about either particle state. And so quantum mechanics has just rectified the problem that was posed by the EPR paradox, because now you can say, well, there is no way I can instantaneously know the state of one particle anymore. Now I have to measure the state of both, and so the information reaches me at the speed of light like it was always supposed to. And so actually entanglement is the solution to this paradox with relativity, and not the problem.
Okay, thank you.
No problem.
So this question is actually forwarded by one of the students from Vivekananda school, but he did not mention his school. Well, name. So actually I am reading out the question on his behalf. Okay. So if you consider the infinite series, alternating series, this is actually a divergent series, right?
Yes.
But the sum of the series is shown to be half. Why? How come it show? This is his questions.
Okay. So this is something I talked about in depth a while ago in one of my other lectures. This is not 1/2. But in certain contexts, you can get something that normally works with convergent series. So here's the thing. Let's say you have method A and method B. For figuring out the sum of a series, now method A can figure out the sum to most series. But there is one series that it assigns a bunch of different values, none of which could be true. And so, it does not return a correct result for this series. Meanwhile, method B, which is less useful for practical applications, does the same thing. It works for all of the series you could try, but it also works for some of the series that you can't try with method A. And it assigns them a value. Is that value necessarily correct? No. Is it mathematically useful? Depends on the context. But this is essentially what's going on behind the scenes. In fact, method B we're talking about here is what we call the Cesaro sum, which is essentially a way to sum a series by looking at the common ratio between the partial sums and seeing what it approaches. So that's essentially how this can be assigned the value 1/2. The useful method, method A, cannot assign it a correct value. That's why we call it a divergent series. But method B, which returns the exact same values as method A when method A works, also gives a value to the sum that method A can't. It's like an extension of method A that's less useful mathematically, but works in more contexts.
If we take the partial sum, if we take the event terms, sum of the event terms, then sum of event terms is 0. Right?
Well, it's a little bit different than that. One of them is 1, 0, 1, 0, 1,
Sum of the
0.
odd terms, that is equal to 1. So if we take the average of this, now considering the analytic continuations, the sum, if we take the average, that is 0 plus 1 by 2, then the sum can be equal to.
Well, yes, it's slightly different than that, but you generally got the gist
If we
correct.
consider the analytic continuation, whatever told, that is absolutely correct. But if I go through this approach, then the result is also half.
Exactly. You've just defined what we call the Cesaro sum, the analytic continuation. So more precisely, you could actually say the partial sums are 1, 1, 2, 2, 3, 3, and so on and so forth. And so what you get is 1 over 1, 1 over 2, 2 over 3, 2 over 4, 3 over 5, 3 over 6, which is the average of all the terms, and eventually that is going to approach 1/2, because every other term is exactly 1/2, and the odd terms approach 1/2 as n gets infinitely large. And so this ratio of partial sums assigns it a value. Is that value necessarily correct? Well, that's up to you to decide.
Thank you.
No problem.
থ্যাংক ইউ
ওকে
আমাদের কাছে আরো অনেক প্রশ্ন আছে কিন্তু সময়ের অভাবে কারণ প্রফেসর বাড়িকে আজকে সন্ধ্যের মধ্যে এখান থেকে আবার গৌরবঙ্গ বিশ্ববিদ্যালয়ে যাবে সেখানে আর একটা প্রোগ্রাম আছে ওখানে রিসার্চ স্কলারদের সঙ্গে তার একটা ক্লাস আছে তারপরে সন্ধ্যায় এখান থেকে বাই রোড দারভাঙ্গা চলে যাবে আজকেই এবং সেখান থেকে যাবে গৌহাটি তারপরে বোম্বে হয়ে নিউ ইয়র্কে সুতরাং আমাদের কাছে প্রশ্ন থাকলেও সময়ের অভাবে আমরা নিতে পারছি না এবার আমি আজকের অনুষ্ঠানে ভোট অফ থ্যাঙ্কস দেওয়ার জন্য আজকে এই মিট প্রফেসর সুবর্ণ বাড়ি প্রোগ্রামের কনভেনার ডক্টর উজ্জ্বল সাহাকে আমি অনুরোধ করছি এবং তারপরে আমাদের জাতীয় সঙ্গীত হবে সবাই দাঁড়াবেন তারপরেই আমাদের অনুষ্ঠানটা শেষ হবে প্লিজ এতক্ষণ আপনারা ধৈর্য ধরেছিলেন ভোট অফ থ্যাঙ্কস ডক্টর উজ্জ্বল সাহা
Good afternoon. We are now at the end of this wonderful session. Now it is my honor and privilege to deliver the vote of thanks for today's remarkable session. We have had the unique opportunity to witness brilliance and inspiration through the words of none other than Professor Subarna Isaac Bari, the youngest professor in the world, a true prodigy. On behalf of Malda College, I extend our heartfelt gratitude to Professor Bari for taking the time to share his insights and journey with us. His lecture today was not just intellectual stimulation but deeply motivating. He has shown us that age is never a barrier to excellence. We also honored to have Professor Bari's father Professor Rasidul Bari accompanying him today. Sir, thank you for your presence in this event. I would like to take this opportunity to extend our sincere thanks to Honorable Vice Chancellor, who actually is not present due to his illness, Vice Chancellor, Honorable Vice Chancellor Professor Pavitra Chattopadhyay and Registrar Dr. Vishwajit Das of University of Gaurbanga for their constant support and encouragement in organizing this special event. I extend heartfelt thanks to our guest, Honorable Chairman of English Bazar Municipality, Sri Krishnendu Narayan Chaudhary, for taking time out of their busy schedule to attend this event. Your presence added immense values to this occasion. I would like to take a moment to express our sincere thanks to the coordinator in India, Sri Pranesh Devnath, and also Professor Snemoy Ghosh for their exceptional efforts and dedication in making today's event a reality. A special thank also go to Professor Pradeep Devnath of the University of Gaurbanga for coordination that ensured the smooth execution of today's program. It is both an honor and a pleasure to extend our heartfelt thanks to our esteemed governing body president, Professor Saurin Bandyopadhyay, for his constant support, encouragement in organizing this event. I also take this opportunity to thank our honorable governing body member, Srimati Shumala Agarwala, Vice Chairman, English Bazar Municipality, and Srimati Chaitali Ghosh Sarkar, Councillor, English Bazar Municipality, for their support and also for their presence in this occasion. On behalf of our organizing committee, I extend our heartfelt thanks to all the guests, principals, headmasters, headmistresses, teachers who have graced this wonderful event with their presence. I also take this opportunity to express our sincere thanks to our respected principal, Dr. Manoj Kumar Boiddo, for his unwavering guidance, constant encouragement, and wholehearted support in making today's event a resounding success. I would also like to thank members of our organizing committee, faculty members, non-teaching staff, technical team, volunteers, and also those who work tirelessly behind the scene to make today's event a grand success. To our students and other attendees, thank you, your presence, attention, and engaging questions. Once again, thank you everyone. I also thank our Teachers Council Secretary and today's anchor, Sri Piyush Kantisa, for his never-ending effort to make it success, to make this event a successful event. Once again, I thank you everyone, and sincerely you, Professor Subarna Isaac Bari, for gracing us with your presence. Thanks a lot.
ধন্যবাদ। এবার আমরা সবাই দাঁড়িয়ে পড়ব। আমি সবাইকে দাঁড়ানোর জন্য অনুরোধ করছি। আমাদের শেষ, আমরা আমাদের পেছনে জাতীয় সঙ্গীত হবে এবং জাতীয় সঙ্গীত গাওয়ার পর আমাদের অনুষ্ঠান এখানে আমরা শেষ করব।
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे